Okay, meeting is live on YouTube. Let's get started. So today I'm doing some docking work to help the rational design folks out a little bit with the Rosetta design protocol. So I've got it started already with this particular plastic ligand. These are 3 different nice dock conformations, all having about at or better than negative 6.0 kcals per mole, which is very nice. The purpose of this live stream now is to show you, I guess, sort of the difficulty in perhaps extending this to a longer polymer. So let's open up Autodock. Sorry, I need to open up Avogadro. And let's open something that's recent. So I have 2pet.pdb, which is this 2 subunit polymer thing. This right here is the 4 subunit one. So you can see it has 4 benzene rings. And the one that I just docked that you see in these pictures is 2 subunits. Did that because that's just easier, smaller search space, and it's just faster. So now you know at least this dock works. And by the way, the active site, you need to sort of specify where this is going to be docked. That was actually interesting to figure out where you should dock this, because there wasn't really much guidance from the literature for this particular enzyme. So I had to sort of use intuition and just look at the surface and see which place looked like it could accommodate a ligand. And these pictures look very nice. This is like a very nice binding pocket. So the worry I have now is if you extend it, just even maybe by 1 subunit, it's then unclear how well the docking will work. First of all, it's going to have more degrees of freedom. That will increase the search space. Second, I don't see any places near the edges here that could maybe accommodate maybe another subunit. There might be something down here that's sort of not visible right now, but we'll see. So I need to edit this molecule by removing some of these, one of these subunits. So what I like to do with this polymer, this is a PET, 4 subunits. You have these 2 carbons on the tail here. This is sort of my point of reference. So one side is this hydroxyl group OH here, and then the other side is these 2 oxygens, carboxyl group. So it's an asymmetric, right? So I like to keep this on the left and just point of reference. Then I need to just remove one of these last terminal subunits. And removing this subunit means removing everything up to here. So this bond will need to break. So I just select all these atoms and I delete them. And then add hydrogens will add that remaining hydrogen to satisfy the bonds there. So this is now a 3 PET molecule, which then I can save as, so I'll save it as 3pet.pdb. So that's that. That's saved. Now the next step is Autodock tools, which if I try to remember what the procedure was, I haven't really used this in a year. Just reviewed the tutorial, but I'll show you sort of the process on how to come up with those input files. So if I look at this Autodock Vina thing. The configuration file requires PDBQT files as input, not just PDB. This includes, I believe, charge information that you need some pre-processing for using these Autodock tools stuff here. If anyone knows like an automatic way that you can do this through scripting and not just clicking this GUI, that would be great. But at least for this application, I just have one structure, so either solution is fine. So okay, I think what I do is read molecule, and I read in, I think it was in one of my downloads. This is sort of disorganized right now. This is the target structure that I would like for OYY. Okay, it's read in. And then, so far we're not even accounting for flexible residues, which actually, coming to think about, maybe for longer ligands, you probably want flexible residues. But in any case, we're going to do hydrogens add, polar only. Just going to add the hydrogens, right? And this is just memorizing from the tutorial, but you do grid macromolecule, choose this macromolecule you have. All right. I'm just going to save this as, well, it's 4OYY for 3 pets. And then this is PDBQT. I mean, it's the same file that I can reuse, just the last one I generated, but I just want to be complete. After that's done, you load in your ligand. So you need to open your 3-pet that you created. And this is the important thing. You can look at all files, or actually PDB files in general. So you see now you can see the 3-pet. The 3-pet is loaded. You can see it has 3 rings. And let's hide. Well, let me just look at ligand, torsion tree. So you can see all the degrees of freedom. Sorry, that's the wrong one. Torsion tree, choose torsions, I think. There we go. You can see it has 21 rotatable bonds. It's quite a lot. For 4-pet, there's 30, I think. And then for 2-pet, there was 12. So this really increased the number of bonds that you can make rotatable, but we're just going to save this as PDBQT. I'm going to save this as 3pet.pdbqt. And we're sort of done with this. But I do want to look at the grid box, because this is really where it's interesting. This is where human rationality can come into play. So the 3 places that's on the active site, I don't think I've closed this yet. 105, 173, and 160. So let's choose 105, 160, and 173. So you'll see now that these residues have been selected. What I want is also maybe show the molecular surface to get an idea of, where we're at. If you try to look really closely, there is like this binding pocket right here. Right, that's where I want the box to be. So if you go to grid box, these are the defaults. And I do have some pre-settings from last time. It was 28 for this one. 16 for this one, and 20 for this one. So that gives you a nice grid box over here. And then the center of that box, X, Y was 3.292, and Z was 4.467. And you'll see it adjusting accordingly. So this sort of covers and puts the serine, which is right here, at the very center. All right. Now with the longer ligand, I'm pretty sure it might take up more space. And in particular, it seems like there's this area here that might want to accommodate some more ligand. So that's the first hypothesis. So that means I should probably expand the region, the search region. Like I don't think here really can accommodate that much more. So keep this boundary as is, but I will expand the search region over here. So maybe 20 and shift this over a little bit over here. Okay. And I hope this will cover this region because 28 for that is quite a lot already. Yeah. I don't know. Let's go back and see sort of where the docking's at. So you can see these two things that pop out. I think that's like corresponding to this region over here. Right, this is the thing that pops out. So this ended about here. Right, so really this search space was not too necessary. So I can move this maybe a bit more to this side to include this region of space, which even if you just look at the ligand structure, if you look at the residue side chain structure, it seems like this is a void that can potentially accommodate some new residue. So let's give this a shot. This is a bigger search space for sure, but we will look at it and see. So nice thing about Colab is this is the 2-pet search space. This is what I defined. You can include really another cell and you just save all of these things and be super visual and clear about it. So a 3-pet search space will be the same. I'll just copy over these parameters. It's the same receptor. The ligand changes to the 3-pet. The output files, let me just remove those output files. So it's going to be all.pdbqt, and it's really the centers that's going to change. So 28, 20, 20. So that's 28, 20, 20. So I have increased the search box by quite a bit. And I've also repositioned the center of the box. So 13.669, 7.041, and then the Z center that I didn't change. So running this will update my conf.txt. There we go. So 13.7, that's updated. So that file, yeah, I don't know why the timestamp isn't updating, but that file is updated. And now all you need to do is to upload your 3-pet PDBQT that you saved, which is the ligand. You already have, or I already have 40YY, which I pre-processed before. See all the stuff in your current directory, and then you just start Autodock. This might take a bit longer than usual. So also the nice thing about Colab is you get to visualize these things on Colab itself. but I can't seem to find a good way to sort of loop over these models with like that PyMol lets you do it. So, I mean, all you can really do is pass it a parameter like that, but it's sort of a hassle. Anyway, this will take a bit of a time to run. And we only have 2 CPUs on Colab. But actually, no, it looks like it's running decently fine. So this is with this search box. I'll keep this window open because I'm suspecting that the first try is not going to work too well. You can sort of visualize these things. I'm going to play around with Chimera a little bit because I know there's a mesh representation there. Or actually, maybe even in PyMol there is one. So actually, let me open up PyMol. There's a really nice graphics representation. I'm assuming, maybe it's not in Chimera. Let's see. Molecular display. Yeah, I guess you can show all these things. Graphics. Yeah, so what I did before was it's flat, but I want the mesh. Okay, I think it's probably this one. Now let's try with Chimera. Haven't really tried this much. So it's going to be in downloads. I'm going to load in, let's see, maybe which structure do you want to load in? Which one looks nice? I mean, this one looks really nice. I think this one also had the lowest energy. So that was in this. But I also want to load in the 40YY file. Okay, let's open up both of these, and you'll see all the confirmations that Autodock searched through, right? I don't actually need the other confirmations, so I only need the 6th run. So there's 9 in total, I think, right? So I don't need anything else but other than the 6th run, which is this one. That's the only thing that's not really great about this one is you have this jutting out. As my assumption here is that the 3rd sidechain or the 3rd subunit will sort of fall in between this groove over here. That's where I set up the search space, and there's really no space here for anything. And this mechanism is really actually mirroring that of other known enzymes where what you've got is the tail of the protein of the plastic sort of hanging around in the rest of the structure, and then one of the terminal subunits with this carboxyl, with this terminal ethyl group here gets cleaved. Let's try to look at mesh. Haven't really figured this out yet. Yeah, what is, maybe I have to select something. No volumes specified. I see, okay, so let me try to, well, for example, molecular display, you could do, okay, so let me turn this off. Okay, and maybe this selects this thing, right? And then maybe now if I look at mesh, no volumes. Electrostatic then? Well, this you can obviously show the surface of. Atoms with non-standard names, really? Oh, you want to delete the hydrogens. Interesting. Okay. Well, in any case, this is a pretty picture. It's a pretty picture. So this is the sort of the groove I was talking about. Maybe it'll fit in there, but this is a very deep groove, which is nice that it fit in. Okay, let's give up on Chimera for now because I know with Pymol you can definitely do it. Open recent 40yy.pdb. All right, and then let's open up all our docked structures. So open recent 1. So that was 0, and this is 1, and then this is now 2. Okay, I will remember to save a visualization state so I don't have to redo this thing from scratch. So I load up all of this. It's really interesting that the lowest energy state is always this thing that's sort of bundled together, huddled, cramped together. In any case, I want to see show as mesh. Beautiful stuff here, right? That looks awesome. Even more awesome if you set the background color to white. And then you hide the chain, you hide the how should I do this visualization? Right, see, this sort of shows you this whole thing. Let me see. Let's copy this. And so this is a new object. I'm going to rename this object. Rename this object as 40yy copy. So what I want to do, let's hide everything. For the original 40yy, let's just show the cartoon. But I want to show it in a very pale gray color. And the new one I want to show as the mesh. Okay. That looks a bit messy, but it's nice if I just color it maybe in the darker gray color. Okay. That still kind of looks a bit messy. Maybe it's because this thing right here, yeah, how do I turn this transparency a bit down? Yeah, it's very intense. If I hide everything, okay. Maybe that's better. It's just the mesh. Let's color it a bit lighter in terms of grayness. All right. And then for, let's say, this thing, I really don't like the licorice representation. So let's loop this over to the 6th structure. And let's figure out a better way to show this. You can, like a line structure, here, hide everything. You could even do this as lines. Well, that's the skinny stuff. Okay, that's sort of a dot representation. You can't really even see that. What about spheres? That just looks weird. But it's look at how tight this pocket is. It's really nice. Okay, let's just hide and maybe show the surface. Right. it's really nestled in there. That's really nice. But I don't know if to like the general audience, if showing this is understandable at all, because they don't really associate this glob with plastic. So what if I color it something like black? Okay. Huh. That's interesting. Might be too dense. Maybe if I do a mesh. Yeah, I don't want everything to be a mesh though. Maybe I like the violet mesh or a hot pink mesh. This is a beautiful pocket here. You know what? This is running. Okay, so I have time to afford. Oh, sorry. Menton AI. You look at this. So, okay, I see what's going on. This is like some coalish gray thing. So they have like a black background. Oh, that looks cool now. And then this mesh is apparently orange. Apparently enzymes are orange. Whoa, okay. This is then copying their design then. Let's color our enzyme sort of maybe in a different color. But orange and black is just this amazing combination of colors. Yeah, let's see what happens if I just copy their color scheme. So like this charcoalish gray thing, and it's this surface representation. And there's no mesh associated with this one. Wow, that looks pretty amazing, doesn't it? But I'm just copying their color scheme. Also, not sure how much you could control these colors on Primal, because there is this lighting issue where they're like shiny. In any case, this looks a lot better than anything else we've really had. And so really then you need to pick a good orientation for this. Right, this sort of looks like a hand. But this sort of looks alien, almost. Yeah, but if you put it like this, sort of, I don't know. Yeah, let's just keep it like that. Shift this, and then make this a bit larger. I don't really need this whole enzyme to be shown. Yeah, but I guess if you want an enzyme, this is where it's at. And also amazing thing is you can do a movie. You can append to it like a scene loop or a camera loop. I think it was this one, right? Where while mutate, right? Yeah, okay. Let's do a mutate over 8 seconds. Well, let's see what happens now. Let's play this thing. Wow, okay. That's a very interesting movie. That's very cool. So if I put this a bit higher up like this, I see. Okay. I mean, it's just sort of copying their stuff, but I think it's a nice visual for sure. It's a very nice visual. It shows you exactly where it is at. Oh, by the way, actually my confirmation is wrong. This thing I'm showing is wrong. It's supposed to be the 6th structure. Yeah, there we go. This is a much better. So yeah, if you do a mutate now, program camera loop mutate over 8 seconds. Ah, I see. It just defaults this to the first state, and then oh, okay, that's too bad. Let me just save this, and I think that docking is gonna be finished. So let's do a draw. Whoa, that's crazy. Copy to clipboard. I know this is sort of useless if you're not presenting this, but you know, this representation looks a lot better than this representation. I don't know if something's going on here with. Yeah, I like this lighting a bit more. Maybe it's just even better to, yeah, let me copy this. Yeah, maybe it's just better to do a screen grab. Than this. Let's delete this. Okay. Okay. Now this is gonna, well, this is almost done. So we can look at those results later. Well, that's a nice docking of this particular structure. And oh, I need to forget to always save the session. So in iGEM, I save this as 2pet docking, and I'll save a primal session. So next time, it'll just load this by default. Okay. Now I do want to talk about this ESM thing. This is sort of off topic, not the title of this video, but this thing just took almost 2 hours to run. And so it's pretty important that we should take a look at what this is. What I'm doing now is essentially scoring these protein solver generated sequences and using ESM likelihoods. So ESM is this massive transformer-based language model that essentially the idea is it's trained on all of known protein sequences. So it's a generative model, and if then that means you can score some sort of pseudo likelihood with this because it's a bidirectional thing. There's no real likelihood, but in any case, it's useful, I think, to see maybe the likelihoods under this model, and this is what we are plotting. So, wow, now that's insightful. This is actually, I was worried that running this is useless, but that's insightful for sure, because higher likelihood, so this is this is the log likelihood, which means it makes sense that it's sort of a negative range. But if you think about this as the log, yeah, this is quite low. But it doesn't really matter the absolute value of this. It matters the relative values. So if you look at this, protein solver has very low sequence likelihoods, unfortunately. But no one has really said that you need a high likelihood for these things to work. I mean, even those things that were recovered in BLAST, some of them had fairly low likelihoods, right? But again, it was this blue curve is sort of the natural distribution in the data of the protein we care about. And then you have these two other generative models that do fairly well. It's sort of near the mean of BLAST. Some things are even a bit better. Both of these were trained on this blue data set. Protein solver, on the other hand, was conditioned by a structure. So this is a very interesting result. I wonder what people will interpret this, how they will interpret this. So let's go back to generative models, sequence-based. And I think no, it wasn't in this. It's in sequence metrics. So you have these ESM results. This was the old one. We can actually delete this one now. This was this was interesting. So now this is an updated version. Very, very pretty curves. This one is really weird, but we will discuss that a bit further. There are actually more sequences that we can score. In particular, we do have some VAE sequences that I do want to get my hands on. So, for example, the VAE sequences that are not fine-tuned. Hold on. Fine-tuned sampled. Just in case, here's a VAE with no fine-tuning as a training, so it's very small. Then fine-tuned. Okay. There's a lot of different experimental setups that we can do here. And so I do want to ask Isaiah. So I see the both So fine tuning just means there's this LCC experimental data set that has those types of fine tuning. Well, it's interesting then to maybe, let's say, download this. So this is the VAE samples. It's interesting that even after fine tuning, you still see a lot of diversity in your sequences. And again, one thing that you should always look at when looking at these sequences is a web logo. And a web logo, fine-tune, sample of FASTA, will just sort of give you an idea of what your things look like without doing any analysis. Let's take a look. That's a very, very nice distribution. And we can actually score this. So let's upload this thing right here. There's actually 10,000 sequences in this. So I'm going to rename this as VAE dot FASTA. This is the pipeline for ESM. You load in some file, a sequence file. In this case, I called it VAE fine-tuned. Oh, by the way, I saved this protein solver PLs. I need to save this just for safekeeping. Anyway, so that's saved. Now I'm off to the VAEs. So I parsed through all the VAEs. For example, this is the first sequence. And I need to make sure that all the gap characters are replaced by spaces, by empty characters. And all the spaces are replaced as well. So, for example, this is the first sequence. This is the pseudo likelihood function that then you can run. Right? For example, here, protein solver PLs that took 2 hours to run. You probably want to save all the compute effort you spent on this. So the next thing is VAE fine-tuned PLLs .numpy, and then we'll add another curve to this already beautiful plot of all of these tools and add a 5th generative model to it. Okay, so things are looking very nice right now. Whoops, I don't know what I did. Oh, I deleted this. Okay. I see. Okay. I don't need that. So this would be the VAE. And then this would be the VAE fine-tuned. Beautiful stuff. Very, very beautiful stuff. Actually, I don't know if this will even finish before I have to leave this video. But this is almost done, so at least let's take a look at some of the docking results and see what happens. Oh, by the way, in terms of docking, there's a parameter that says number of modes. So that's the number of maximum number of structures the docking output can output. I think maybe before I changed this up to like 200 something, just because it was just not finding the right one properly. But at least it's good. Cool, 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 very cool. In terms of protein solver, that was an interesting finding. Analogous to protein solver, I'm also training an Ingram generative model. I'm actually not quite sure how many epochs this has done, but what we see here is, so this is the paper for the model. That's what you call Ingram model. They report that their best test loss was 6.85, I think. Now this is about 6.85 already. Oh, by the way, I'm using this variant that they have, this MLP thing, the message passing, I believe this is the thing. Yeah, it's about 6.55. So if you look at the validation loss, it's pretty close to that already. But although some of these batches have a bit higher loss at the moment, but right now it seems stabilizing. This already 60 something thousand steps already. And oh, Vina is done. Beautiful. All PDB2T. This is promising. Right, something around 5 already is promising. Maybe in the future I can update and even increase that to 30. But let's just take a look. So I need to convert this to a PDB. And then this can be downloaded. And then we can sort of load in our visualization states from before, the one with the mesh. Oh, that actually might not be so helpful. So let's just open these structures by itself. So it's going to be this one right here. And I like to zoom to all just to make this easier. Okay, you can see now you have 3 rings. And the initial hope was, I see what's happening now. So this ring isn't really coming in this way. And that might be the unfortunate case where I've misspecified the docking location to be too far off in that direction. And it's just wrapping itself around over there. Well, the active site's here. Or that's where the steering is. So that was, I guess, sort of the intention of this video, is just to show you the difficulty of doing docking in general, but especially for large ligands. And these parameters require a lot of tuning. So it's good that I didn't close this, because what ended up happening was all of those things clustered over there. So let me reset my box to this size and then maybe try to accommodate based on that again. So 24, 16, and 20. There's 24, 16. Oh God, this doesn't want to work. Sure. And then 20, and these 3 things, XYZ, 3.3 approximately, and 16.2. So this yielded amazing results for the two subunit case, right? But unfortunately, it did not yield as good of a result for those other things. Now let's see the pocket. It started here. So I think the start area is still, you should keep this part. I don't know how much you want to extend. I mean, I guess this is fairly constrained. Let's just try to keep, there's sort of the 2 extremes now. If you want to just keep everything the same as before for the 2 pet stuff. All right, and obviously you need to change this, and then maybe 30 modes for this one. So let's just keep it like that and see what happens, because obviously now the first run was terrible. Again, this will take a while. That's the thing with docking. You're not really sure how to put your grid box. Although this sort of tells you, but it's not too clear. I guess if this doesn't work, if the ligand tends to bundle together again with this grid box, what really should end up happening is instead of extending this grid box, maybe I can even put the Z center down a little bit to make it, force it really onto the surface of the protein. And yeah, I mean, I think this part we should really be able to accommodate that already. If you expand that to 20, I don't think that's really a good bet. Maybe 18. Yeah. This might be the next one to try. So it's just trial and error, a lot of trial and error, and then maybe push this a little, just tiny little bit, because before I had maybe too far to the right. It was 16.2 Yeah, it was 16 point high C. Yeah, it really still needs to be centered there. We'll see what the result is. In any case, I'm sort of unclear about when I should stop this training. The default is 100 epochs. And I'm not even sure how many epochs this is finished. So, maybe just a place to improve this code is instead of printing this all the time, utilize mask. Yeah, instead of printing this all the time, okay, this is for just statistics. But what was, I think this was did I print this? No, this was there before. But instead of printing this all the time, I'd more appreciate yeah, something like that. So TQDM, I think the import is like, goes like that. So it'll show up like a nice progress bar or something. That's just for next time when you're doing training, just so it's not this wild mess. Okay, I think it has been productive. You identified the active site of this enzyme, and then I made this visualization, and I showed you the statistics for ESM. And eventually, at the end of the hour, hopefully, we will get somewhere with the VAE stuff. So just in case that I won't be here, the video won't stop, or this will still go on. And it'll generate the plot before the runtime times out of stuff. So this is running, which is fine. Not sure if you guys want to see the Ingram stuff, because if you want to see the Ingram stuff, I have to stop this training, which I'm not sure really exactly when to stop. So yeah. By the way, this is not fine-tuned on any data set. This is just on this cath, this massive cath data set. Because right now train, oh shoot. So I messed up big time. Because train S2S, oh boy. args.file data. Did I mess up? For example, arg.file data. This is chainset.jsonl. That didn't really change. No, I don't think I messed up, because chainset, for example, I can take a look at what that is. This is this 400 something megabyte file, and I'm using chainset splits, which is the original splits. Mm-hmm. But I might have messed up in the fact that, for example, this is train S to S, but there's an original train S to S, which does the data set splits that I don't do. Hold on. Let's compare. So these two the same up to line 24. Okay. Okay, I don't think I messed up. Okay. Well, in any case, I don't know when to stop this. What's happening is that in log, this sort of plots, for example, there's a lot of plots here. Yeah, maybe this will shed some light on what iteration. So this is the step. Oh, you know what will really reveal to us what's going on is if you cd into this folder right here, or this folder, copy path, cd into this folder. This counts the number of files in this folder, 223. And we are at, oh, that's very nice, actually. We're at epoch 95, and there are 100 epochs in total, so we're almost done. We're almost done the training. So it seems like for every epoch, there's about well, actually, you can't really tell from this one. For every epoch, there is about, I don't know, epoch 90 is this one in 91. Okay, so for every epoch, there's about 1,326 steps. Which means when this is at about just under 70,000, it will be done. Or around 70,000, or just over 70,000, it will be done. So let's patiently wait for that, because this has already been running for almost 5 hours now. And we will obviously then save a bunch of these checkpoints to file, and then we can just, it's blast off from there. Because what's the next step for that is, there's two options. You can either directly do this test redesign on some particular epoch and step, and this will test, or what this does is it designs the sequences to fit onto some desired backbone. And then you can sample like 1,000 sequences from that and see what happens. The other thing that you can do is, using this model as the initial parameters, fine-tuning it on a set of backbones that you really want it to be accurate on. Not really sure about the best way to do that yet. So far, we've been settled on trying to, well, we've parsed the PDB IDs for this particular cath class. I think it's 3 40, yeah, this one. This particular cath class, or sorry, superfamily, I guess, in this case, it's domain alpha beta hydrolase fold. About 3,000 different domains in here, covering just under 2,000 PDB IDs. It's a very interesting idea, but this is then, there's going to be a lot of duplicate structures in here. And unfortunately, the other thing is some structures that they upload on the PDB are like bad structures. By bad, I mean not really enzymatically active. For example, 6-THT. This is a quintuple variant. The good enzyme is just actually 4 mutations. It's quintuple because the additional mutation that they add to it removes one of the catalytic active site residues, which is very bizarre. Not sure why they did that. But in this case, what the model is going to learn then is it doesn't know about that. It's just going to say, well, at these positions, maybe you want to do an alanine instead of a serine because that's what is in the data, which is terrible. So one way to correct for this, that might be a project of its own, maybe for next weekend, is when you're generating these sequences with this Ingram model, so that's going to be the code in test redesign. Currently, it does it auto-regressively through code that I don't really fully understand yet. So here it is. It is, where is it? Well, right now it's just calling model.sample, but if you press F12, sorry, what is going on? Model.sample. I just lost it. What happened? Here it is. This file is in struct2seq.py, and then there is a sample function in here all the way to the bottom. This is an autoregressive decoding of a model. You're given a structure, I believe, and lengths of sequences and a temperature. And then you're asked to decode. The thing with this, unfortunately, is what's happening with this decoding is that it doesn't care about, for example, it could just put like a alanine or whatever it is at the catalytic residues, and that's something we don't want. Somewhere in this code, I need to figure out how to condition on already observed residues. That might be a lot harder than I think, because if you look at their paper, when they're doing the decoding, the information for this residue comes from the sequence of everything before it, but both the the structure of everything that's around it. So somewhere in this code, for example, the encoder is unmasked self-attention. And then the decoder alternates masked self-attention. Yeah, I need to like unravel what these variables mean. But I can see sort of that there is an autoregressive mask. And this is probably you're applying it to everything that came after it. All right, mask attend, BW and FW. I don't know what these variables mean. Stale relational features for future states. Update relational features for future states. Well, so BW is just everything that's in the mask, autoregressive mask. And FW is everything that's not. So it's a complement. And this ESV encoder looks at those things that are not in the autoregressive mask. So if I assume correctly, the masks are 1 for residues to keep. So then this is the autoregressive mask. So FW are those things in the forward, and BW are those things in the backward. So the backward stuff is the thing that you actually want to keep in terms of your sequence features. Maybe this thing right here. And then mask FW is those structure features sort of in the future. So maybe this is the structure feature. I don't know. Well, it looks like this and this thing, cat neighbor nodes. What is the difference between HET and HEST? So T is just this iteration, this particular iteration. And by iteration, you mean you're doing the decoding by nodes. So this is a teeth node. And it's looking at the hidden representations of your edges. Okay, and this makes sense. This is just the hiddens. These are just your edge embeddings, and these are your node embeddings. All right. So you go over your encoder, and what you do is you concatenate your node embeddings with your edge embeddings. And this is probably just a tool for you to determine which of these edge embeddings are around your nodes, just a graph structure. So you get this concatenation of EV, edge and node. And then you apply an encoder layer to it, which then you get new node embeddings. So this variable is updated, which then it's fed back into this, but then the edge features stay the same. Then the decoder, this operation is here. You go over the decoder layers here, and this is the application. So the layer here is applied to HV stack. Okay. Apparently this is just a stack. I guess this is for efficiency. And these are zeros. So starting with HV, what's happening with HV? HV at this point of the code is the encoded node representations. And S is supposed to be the sequence for all the nodes. So this starts off as zeros. And this also starts off at zeros, right? And also this stack. You go over all your nodes, and you get the edge indexes, edge embeddings for this particular node. And then you want to concatenate somehow this zero stuff with your edge embeddings. But this is going to be updated. right? This is the sequence information that's updated, because self.ws on st, this gets you, well, st is already this multinomial. This samples from the 20 amino acids. Not sure what ws is. Is this embedding thing? Interesting. Why is it applying an embedding on an embedding? So an embedding goes from vocab to hidden dimension, which makes sense. I see. So this is, I see what's going on. This is the discrete stuff, because you already sampled from a multinomial. This is a discrete amino acid label, which then you embed, and that's your HS. These are your amino acid embeddings. And this S is the actual discrete sequences of those integers. And that's what you return at the end. This first colon here, I think that's for the batch, because you can do this a batch at a time, I think, which is crazy to me. Yeah, for example, yeah, n batch, that's the first dimension. You're doing for a batch at a time. In any case, that's sort of understanding what this means. Now, what about the decoder? Decoder is the super important part, because sure, you have an encoder. Unmasked self-attention means you can pay attention to anything you want. But the masking here is the most important part. And in fact, now this is actually, now I've decoded how to customize this model for the case if you want to fix certain residues to be something of interest. All you do is, instead of sampling autoregressively, so instead of doing this type of iteration, instead, your initial thing isn't just a bunch of zeros. I think all zeros is all alanines, right? 0 is the index or alanine or whatever that first amino acid is. So instead of it being all zeros, what you instead do, well, sure, you can start with all zeros, but here's the modification. Set and I put subset. So this is really where you can customize this function, because you could be like, if you want, let's say, serine, I don't know, let's just take this as an example. If you want serine 105 to be there all the time, ideally, the user input would be take the form of something like a 3-letter code, or maybe even just a 1-letter code, and then the position on the structure. But even better, this doesn't have to be just 1 letter. It could be a list of letters. So it could be a list, for example, either it's serine or methionine or cysteine, I don't know. For example, it could be a list of residues at a particular residue position. So just a doc, like a mini doc string, is going to be S at all batches. Well, this really needs the fact that you only have one structure in your batch. So n batch is equal to 1. 105, this is very tricky. It might be just 105 minus 1. So that thing is going to be, let's say, AA to int, some dictionary that maps AA to integers, S. Something like that. So this is the preconditioning step. Then instead of this loop, which essentially goes from the beginning of the structure to the end, following along the chain, there's no reason why that might, like you would want that really to be the case. In fact, I think even in protein structures, let's say if you look at 4EB0, if you look at the PDB, you have a column in the PDB that there are two numbers here, and there's one number that's the occupancy and the other one that's the B factor, I think. B factor, I think is that last column, right? I read it was column 61 to 66. Yeah, it's this last thing over here, and that's the temperature column. So temperature factors, if we were to hold an atom rigidly fixed in one place, you could observe its distribution of electrons. Image would be dense, while these motions result in a smear of the electron density. The amount of smearing is proportional to the magnitude of the value. Values under 10 create a model of the atom very sharp, indicating the atom is not moving very much. All right. Values greater than 50 indicating that the atom is moving so much that it can barely be seen. This is often the case for atoms at the surface of proteins where long side chains are free to wag in the surrounding water. So that's very insightful, because really what could be just considered designable, of course now the Ingram model is done, and you have a beautiful test perplexity here. So apparently this is the best checkpoint. Log best checkpoint epoch 73. Let's download that. So we can do a redesign right now, right? H128 MPNN message passing neural network. Instead of going to checkpoints, we are going to just load in. You know what, the easier way to do this is I'll just copy the path here, right? And then file data is, sure, it's going to be that. Chainset.jsonl, actually, I have a different chain set. So if I look at my data set right now, this chain set is the Cath chain set. So let's upload that. So I'm going to upload that and make sure that I'm using the new chain set. This is the one where it's that Cath superfamily. Okay. Cool. So this, let's just have that upload just fine. But I do want to talk about these B factors for a little bit. If you allow so many positions to be designable, probably what would be nice is if you can yeah, if you just even look at this, the PDB display, yeah, let's just display this. You can see, all right, 24. That's fairly high. And then you have these 20s for arginine. And there's another 24. Just saw it right here. Whoa, this leucine is out there. Serine 165. It's not extremely flexible, but it is somewhat flexible. And the most important thing, I think, is actually this oxygen here. That's fairly flexible. So my idea, my take on this, maybe sort of a naive take, is that the ones with low temperature factor are the ones that determine structure. And the ones with higher temperature factor can be safely designed. So this serine, I don't think it's part of the catalytic, well, maybe this one is actually. Oh, that would be super interesting if this one is. I think it's 216, right? Is this right? In any case, we should be visualizing this by B factor, or the temperature factor. And keeping the catalytic site untouched, the remaining residues you could potentially allow designable, those ones with like poor B factor. For example, this one. A nice positive control for this theory, probably already recorded somewhere else. For example, this tryptophan, a very tight B factor. Very rigid. You really don't want to change that. And this is tryptophan 259. Oh, you know what would be super interesting to see is how the B factor correlates with the first order statistics in an MSA. All right? That's sort of like a new research direction. Where is my notion? See this tryptophan right here at 224. It's this one. There's an offset. So it's serine, tryptophan, methionine. Serine, tryptophan. Yeah, it's this tryptophan right here. It's highly conserved in this logo. And in fact, it's highly conserved in the blast results as well. So I really wonder. But that also might not be the case, for example, for this histidine back here. This histidine is about 20 residues back. Let's look at the histidine about 20 residues back. Here's a histidine. See how it's not the case for this histidine, right? Especially for one of these carbons. Fairly high B factors. So yeah, let's not waste time doing that, but it's just interesting to see. Active sites are flexible. But then that just probably means this tryptophan is a structurally determining factor. Active sites should be flexible. Okay, let's run this because I Well, let's see what happens. Right. Okay, basically the thing is not loading properly because in test redesign.py, I think the model initialization of the model is from setup CLI model, which is from this util file. I need to specify something with these mpnn thing, --mpnn, because that was the argument that I used here. CUDA seed. Here, let's put it here. --mpnn. I used the message passing one because they said it was the better performing one, even though their graph attention mechanism was the one that is the innovative one. You can see this running without a problem. Okay. Experiments. Designs. This was just created. Test. I think it's this one. Alignments. And so I'm doing tests on these two structures. Let's download. Let's just download both of them. For 4B0. Wow. That's a beautiful, beautiful file. Although you do see quite a lot of repetition. So that's the native. And then these are all the stuff here. What is the score, by the way, in this test redesign? It is native score. What's going on? Oh no, there's another one here. T equals sample equals. This is seek. Oh, score. What is score? Scores. What is scores? Negative log probabilities. Okay. Not bad. You could definitely sort these, but that's not bad at all. And let me look at the web logo again. So this was with the VAE fine-tuned, right? Let me save this as VAE on the LCC 5000 VAE fine-tuned. And now let's choose this one. This is the protein, this is Ingram's graph model, and that's amazing. I love it. I absolutely love it. This is amazing, absolutely amazing. Although that tryptophan is missing. You remember that tryptophan that came right before the M, around somewhere here? Where is it? It's gone. It doesn't like to have the tryptophan there. That's the interesting thing about these graph models. The protein solver one also doesn't like that tryptophan. All right, and it just pops up these weird new residues like R. Well, at least the D is there, at least the H is there. That's very impressive. C and C, very impressive. D and H are both there. I think it was this D. There's a serine. It's preserved. That serine is preserved. There's nothing else other than the serine at 130, which is, I think, the catalytic one. That's very promising. Absolutely very promising. So let's rename this so it's not going to be lost in file naming land. Ingram epoch 73 on 4ED0. And just for reference, this is Ingram epoch 73 on 6EQD. So those are the sequences that this has generated. Now, here comes the cool part. I can score it with ESM. Right? Oh, ESM is like a proxy, but still a nice proxy. All right. Oh God, this is gonna take 1 more hour. Okay, so Vina is done. Really, really curious about what this is, but it doesn't seem like it did better than my last run. Actually, how long has this stream been going along? Oh, 12 minutes. Really? That was just 12 minutes? It felt so long. Great. Let's download all. No, not on that one. It's this one. Yeah, file management is a pain right now. Okay. I mean, worst comes to worst, you just do that one with the 2 subunit one, which is already looking amazing. But it would be really nice to get the 3 subunit one working. So you go to downloads, look at this, and see what happens. So zoom all. Here we go. It is very tightly squeezed in here. There doesn't seem to be a one where it's sort of flat. Oh. This is probably the only one. Let's take a measurement. Before the measurement, I need to look at this serine and then show as licorice, right? Just because I need to measure the distance between this and, oh, I think this is a very nice dock then. But 13, structure number 13 doesn't have that good of a binding energy. Maybe you can optimize this a bit more. Also, I thought there was another option in here in Vina where you could do local only. Yeah, I think that should be the next try. I think I did this. So what happens is all you need really is some starting point like this, a very nice starting point like this. It doesn't have the best binding energy, but using this as a starting point and then doing local only, that's going to be a lot better than without this starting point at all, which is what we had in the first place. But in any case, let's do the measurement. So measure the distance between this and this. Beautiful stuff. 3.4. I think we got it. I think we got our hit. And so let's just make a note of this. Which file is this? All for model number 13. I will eventually name this a bit better, but I'll just take a look at maybe the next few models. None of these look that great. I don't know, maybe this one. It's very interesting that that atom is close, but everything else is just wild. And then that's the last one. Okay. So it's also nice to see what kind of conformations can go in this grid box, which sort of suggests that if something can even go here, it suggests that, yeah, I don't know. We'll just keep the same dimensions and then do local docking, so local only for the next round, which won't be in this stream. It's already way too long. So for example, where am I? Here, right? So adding this option, I need to be more precise then, because for this option, you would need this particular model as the starting structure. Okay, to conclude this live session off, let us lose this, show this as a surface. Oh, I clicked the wrong one. Hide this as a surface, but show this as a mesh. And then hide the cartoon. And I want to color this mesh again by orange. And maybe this is a nice representation after all. You actually see, I don't know how much better you can improve this, because this is very close to the surface, right? This is fairly close to the surface. So then that might suggest that there might be space actually here. That could be another thing to try. So either do local docking on this one, okay, which I will try, or you just change the grid box entirely and allow the structure to explore this region of space here, which would be interesting. And then compare the binding energies to sort of see, I mean, even in this pocket, right, if you were to allow something this big in around here, it would be attached to this. So this will come down here already. And then so this would still fall over there. So yeah, I'm not too sure if this is a good pose, but we will see. So this right here, if I show as surface and color it as, I don't know, yellow or wheat, that just looks weird. Yeah, so actually right now there's some hydrophobicity exposed here now. I'm not sure if this, yeah, it's worth a shot. It's definitely worth a shot. But in any case, let's end this stream off by taking a picture of this beautiful thing over here. In fact, I don't need to do, I can do a free cam. Or, yeah, whatever. I mean, let's just take a picture. Maybe here's an, yeah, let's just take a screenshot. Beautiful. And then put it on Notion. I have lost Notion. And then we're going to end the stream right after. So docking. We've had some pretty successful docks so far. So this one is minus 5.0, just to be clear. And then this one right here is minus 6.0. So beautiful. There we go. Next time we'll see if there's a pocket there that we can exploit. But so far, so good. And thanks for coming.